everyone, welcome to another video on induction machines, and today we are going to look at characterization of induction machine. Very important procedure that all of us need to know, because when you work with induction machines we will need to know the parameters. If you want to, let's say, model it or see if the design was proper, then we'll need to test and verify if these parameters are aligning with what we want, and then we can verify performance, right? If you want to simulate, build a model, right? So things like that. And very similar, the procedure is very similar to transformer characterization. And I hope you remember this model that we have been talking about. And here we are showing, this is the per phase model, and we are looking at VAS. We have IAS, and these are AC, right? These are AC. And then we are referring to as a base frequency. Typically, that is the synchronous speed that comes with the machine. And we are giving the parameters based on that frequency. Okay. Of course, if you want to ignore that, you can do that, and then they will be in J omega E inductance. Okay, because these parameters are going to be omega B times L or LLS, right? So once you cancel out, you have J omega E LLS. Okay, very simple. And the goal today is actually to find or determine these parameters experimentally. And I'll use a sample set of data to make sure you guys see the calculations of those values. All right. So let's get down to it. So we have three tests that we're going to use before I proceed. We have a DC test, no load test, and a blocked rotor test or locked rotor test. All right. And the data that I'm taking are from the book Analysis of Electric Machines by Professor Krauss, Rosenchuk, and Sudoff from Purdue University. And this is a very good book to have with you if you are working in this field. There are other textbooks too that you can refer. More or less, they follow the same principles that we discussed. Okay, and here are the data that we collected from each case. From the DC test, we apply a DC voltage phase to phase, and we measure current. Okay, and the no load test, we are applying, there's no load on the shaft, and then we are applying a voltage, we are measuring the current and the power at a given frequency. And here we are doing a locked rotor, or the blocked rotor. BR is for blocked rotor test, and we're applying voltage less than the rated voltage because you're in a stall condition and the frequency is somewhat lower too. Okay, so let's dive into the procedures. DC test so the stator resistance. So we're trying to find the stator resistance, RS. Okay, and you'll have a current limiting resistor if you want to, if you don't have a controlled source, voltage source, and we're applying the voltage phase to phase, and we are measuring current, and we are placing the voltmeter after the amp meter to avoid any drops from the amp meter. Okay, and the machine is at a standstill. All right, simply when we have our measurements, we know VDC, we know IDC, right? And then we can find our stator resistance. Very easy, very simple test for resistance. And this is the phase resistance, okay, not the line to line. Now, going into no load test, we are basically trying to obtain XLS and XM. Okay, on the stator side, we have the leakage inductance and the magnetizing inductance. So the no load test will help us identify them. Okay, so in order to perform that, you're going to need power meters, two power meters that we need to connect in the following way to measure power from this phase and this phase with this voltage, and the sum of the two will tell us the total power going into the machine. And in this case, since there is no load connected to the machine, the total power applied is going are the contributions of the losses, right? The losses of the machine, right? The different types of losses are, you're going to see copper loss or ohmic loss due to windings. You have current flowing through windings. There's going to be a loss there, and then there's going to be some core loss in the material, and then depending on the type of frequency, like an inverter if you're using, you're going to see other types of losses too. And of course on the mechanical side you will see some form of mechanical losses. Now keep in mind, there's no load on the shaft, which means this is going to be rotating at or close to the synchronous speed. So be very careful to stay away from the shaft when you apply this speed, okay, when you perform this test. Now in the stator, if you assume all the losses are in the stator because there is no field on the rotor as we are operating close to the synchronous speed, then the total losses are going to fall under this category. Okay, that's the total losses. Now, if you think of the total losses, you have friction, windage, core loss, which is equal to the total loss minus the copper loss, right? The losses, these are the factors. So the total losses are friction, windage, core loss, and plus copper, and then we take that to the right hand side. That's what we have is the total power minus this gives us the leftover losses. Okay. Now in induction machines, since they have smaller reactance XM in comparison to the resistive component, we can apply this rule because the smaller impedance in a parallel circuit dominates, right? Since XM is smaller, why is XM smaller? Because when we need to generate large torque, we need to have a smaller magnetizing inductance. Okay, we need to pass a lot of current to generate a lot of magnetic, to generate flux, right? Therefore, the XM is going to be smaller. And therefore, what we can do is using the equation, no load divided by √3 INL, we can capture just the leakage plus the magnetizing inductance component. So let's refer back to our circuit diagram trying to clarify this. Okay, so let's see if I have my diagram. There we go. So in the no load case, the current in this branch is 0, right? Because there's no load. And if so we have the parallel resistance here, but this resistance is very large compared to the inductance or the XM of this circuit. Therefore, in the parallel combination, the smaller one dominates, right? Therefore, when we consider the inductance, the dominating portion is going to be these two inductance values. All right. Therefore, we can come to the conclusion that from the no load test, we can approximate XLS plus XM to be this resistance amount. Okay, this resistance amount. So now we have a relationship for the combination. Okay, and then we can find RS using this equation too. All right, so going into the locked rotor test, right? So previously we looked at the no load test, which we focused on the magnetizing inductance and the leakage on the stator side. With the locked rotor or blocked rotor test, we are trying to obtain rotor side parameter. Okay, and then if you refer to this equation, now what happens is when you have the rotor locked, this circuit dominates. This this circuit is going to dominate. Okay, remember S is going to be 1, right? S is going to be 1. Therefore, this is going to be very small. Therefore, this circuit will dominate, and the magnetizing circuit will negate out. It won't be as significant. Okay, and in this case, if we know VAS, IAS, that means we know the whole path, resistance in the whole path, and therefore we can now subtract those components and extract these two parameters out. Okay, so that's the idea. We again, similar method, we are setting up to apply three-phase voltages. The machine is locked, therefore use lower voltage than the rated, okay, and also lower frequency, but we have to consider that in the calculation. All right, okay, so during stall, our magnetizing flux is much larger, therefore the smaller terms will dominate. And from this, from the magnetizing reactance power measurement, you can obtain RR prime. We know the total power loss, therefore we can write the power loss in this form, RS plus RR prime, but we know RS from our previous DC test. Therefore, the only unknown is RR prime. Okay, so we have our RR prime, and then very simple test. Since we know VBR, we know IBR, the voltage applied, and the frequency that we applied, now we can find the magnitude of the total based on the measured values as well as the theoretical values based on the circuit, right? And then remember, we are using 15 Hertz, so we have to consider that in our calculation. And the magnitude, this is a complex number, that's going to be equal to this. What are the unknowns? The only unknown here is this, right? We know this, we know this, we know this. So now we can extract the unknown parameter, XLR prime. Okay, so this way we can find all the parameters that are crucial to model the induction machine. Okay, we had 3 tests. We looked at DC test, no load test, and the block rotor case. Each case we identified or we highlighted certain part of the circuit just to capture the effect of that, and then we obtained the values. Okay, all right, so now we know how to characterize an induction machine. Please feel free to let me know if you have any questions or comments. Okay, thank you.